In this video, I want to introduce Boolean logical operators. So these are operators that will help us refine our conditional logic. Using them, we'll be able to express more complex conditions for our if statements and our switch statements. So the three that I want to introduce are and, or, and not. We will get to them in a second, but before we do that, I want to back up and just talk about operators. So we have seen other kinds of operators already. So we had the plus operator. So when we put 2 plus 3 into a C# application, those two numbers are added together and we get 5. So you can think of operators as functions. We've got this plus sign. It takes something on the left and something on the right, and what it does is add those two together if those things happen to be numbers and give us back the result. We also saw that we could concatenate things. So if we had a string and we added another string, this would do concatenation and we'd end up with one string with those two things added together. And we also saw that we could do comparisons. So we had the equality operator. So we could say like is 2 equal to 3? And this turned into a value of false. Or we could ask is 3 greater than 1, which would turn into a value of true. So these new operators that we're going to add into the mix are going to do something similar. We're going to give them some inputs, and they're going to turn into a true or false value. So that means they're going to be really useful for us in our if statements and inside of our switch statements. So I want to pull up the documentation page here from Microsoft for the C# language. And we can see a couple of them listed here. So we have the Unary, meaning that there is one input that it receives, not operator here, which is an exclamation point. We have the binary, meaning that there are two things that you give to this operator, and, or, an exclusive or, and then binary and a similar and or here. So we're going to really be focused in on the not and the 2 ampersands and 2 pipe symbols here for and or. So like we talk about with this documentation, this was not written for an intro to programming class. It uses a lot of lingo that is common in programming, but it is not necessarily beginner friendly. But it is really useful to sort of stretch ourselves and try to read this documentation and make sense of the bits that we do understand. So here, this first one, the logical negation operator, exclamation point. So it's telling us the unary prefix operator. So prefix meaning we put it before the thing that we want to negate, computes the logical negation of its operand. So it's going to take the logical opposite of whatever we give it. So if we give it true, then it's going to turn into false. And if we give it false, then it's going to turn into true. And we can see a little example here where they have a Boolean variable past is false, and then you can print out what is the result of using that operator with our past variable, and it turns to true. And if you said not with a Boolean value here, that's going to turn into false. And if we fly down to like the binary conditional and here, we'll see a similar description of what it does and also a note that it's doing something called short circuiting and comparing it to the logical and operator where you only use 1 ampersand. To be honest, this example is one of those ones that I feel like is not written in a very beginner-friendly way for us to talk about. So we'll maybe refer back to this after we get some code onto the page and get some things running. So I have a Visual Studio Console application that I just created here. It is a .NET Core project, and we're going to use this to test out some of those operators. before we jump into it, I'll just let you know that some of these examples are going to be a little contrived because we're going to try and imagine that it's in the context of a larger application. Once we get all of them under our belt, we'll be able to use them to do a little bit of like a rock, paper, scissors game revisited using this conditional logic. So first thing I'm going to do here is I am going to, because I'm going to be using the console a lot, bring in the console static class up here. And then I just want to print something out. And make sure my console window stays open. Hit play, make sure that this is working. Looking good. So now that we have our scaffold of our console application set up, we can just start playing with some of these operators. So we'll start with the not operator, which is the one we just saw, or the logical negation operator. And we can say that it's a unary operator, meaning that it has one input that it's given. So let's imagine that we are making some kind of exploration game, and we need to keep track of whether the player has picked up a map yet. So we'll say we'll start this value off at true. Let's print out that value. And let's go ahead and do the same thing, but we'll flip it here. So we'll say not has map. So since this value is true, we should hopefully see true, that they have the map, and false here, not has map. Has map true, not has map false. And if we flip it, we would see the flip show up in our console. Has map false, not has map true. So you can also express this, if it's easier to think about it this way. What we're doing here is expressing this, checking whether has map is equal to false. So these two should be equivalent when we run this now. Not has map false, not has map false. Okay, so we can see that value. We know that this not operator is just flipping our Boolean. So we can actually use that in a conditional. So imagine we're making this game, we're tracking whether the player has picked up the map or not, and we need to print out some message if they don't have the map. We can just say not has map, right line, you can't get out of the maze without the map. So right now, because we have the map, nothing will be printing out. But if we go back and flip this to false, this condition is now met because we do not have the map. So we should see our new right line print out. Can't get out of the maze without the map. And like we saw here, you can rewrite this condition. What we wrote is the same thing as saying this, not has map is equal to this, has map equals false. Okay, let's do the AND operator. And this is binary, meaning that it has two inputs. So if we think back to when we were making that virtual pet simulator, maybe we would be keeping track of the pet happiness level and the pet hunger level. And for the sake of this, let's assume that our numbers go from 0 to 100 for both of these. 100 is really happy, and 100 here would be really hungry. So this pet is really happy and not very hungry. So in our kind of virtual pet game, we may want to give feedback about like how the pet is doing, how well you're taking care of this pet. And we want to give some feedback if the happiness level is really high and the hunger level is really low, that you're doing a great job. Otherwise, we'll like prompt the player that they should take better care of their pet. So let's start out again by just printing something out here. So we just want to see a true false value here. True if they're a good parent, false if they're a bad parent. And so we can put the conditional that we want to work on here. So let's say we want to make sure that the pet happiness level is greater than 80. If it's greater than 80, then, you know, great parent. So this is just using what we've done before. So prints out, we see true. And you know what? Let's duplicate this. Let's put both of our conditions here. So let's call this happy pet. And we can say this is a satisfied pet. So for the satisfied pet, let's say that the pet hunger needs to be less than 10. Okay, so our pet is currently happy, currently satisfied. What we're trying to do is express that we have a good pet parent here by combining these two things. So we want to ensure that both the happiness is greater than 80 and that the hunger level is less than 10. And that's really easy with the AND operator. So we can drop in AND here. And zoom out slightly to get this all on screen. So what the AND operator does is return true only if both conditions are met. So here, because both of these individual conditions should be true, we should see that we are currently a good pet parent. True, true, good pet parent. But if we go ahead and make our pet 50% happy, this condition is no longer true, so we've failed our check here. And is expressing that both of these must be true for us to get a true value back. Since one of these failed, we'll get a false value back. So we've got a unhappy pet, which means that our message down here about being a good parent would be false. And let me comment out this code so that we don't have all this map stuff printing out while we're working. So now we could turn this into branching logic. So we could take our condition that we were expressing here, and instead of printing it out so that we can inspect the true-false value, we can use it here with an if. So if the pet is both happy and not hungry, then your pet is doing great, good job. Otherwise, you should pay closer attention to your pet. So here, because we have an unhappy pet who is not hungry, we need to pay closer attention. But as soon as we flip our happiness level back up here, so if the happiness is 85, we have a happy pet, and we have a satisfied pet still since the hunger is at 0. So that means that down here, we should see your pet is doing great, good job. pet is doing great. Good job. So even though the AND operator is a binary operator, meaning that it takes something on the left and something on the right and turns it into a true/false value, we can chain multiple together. So let's say we wanted to also store like sleepiness. So a value of 100 would be like that pet is super exhausted, and a value of 0 would be that the pet is not sleepy at all. So maybe we want to integrate that into our check here. So we could say, and pet sleepiness is less than 20. So again, this is by chaining them together like this, the kind of order of operations is that it's going to go from left to right. It'll check this, and then it'll combine that with our pet sleepiness check. And the way to interpret this whole statement is that all three of these conditions must be true for us to see that our pet is doing a great job. If any of them is false, then we'll end up down here. So right now, our happiness level is greater than 80, so check, we're good. Our hunger level is less than 10, check, we're good. Our sleepiness level is 100, so this is not true. So we should see a message about having to pay closer attention. You should pay closer attention. But then, if we go ahead and drop our sleepiness level to 10, we should see your pet is doing great. Good job. All right, we have two of our logical operators down. We have the not and the and. So now we'll learn about the or. And this one we saw was also labeled as binary. So our and allowed us to express that multiple conditions must be met. Our or operator is going to allow us to check that at least one of the conditions has been met. So let's comment this out. We'll have that for future reference in our code, but let's start working on the next one, where, remember, we were doing that clothing recommendation engine where we wanted to get the temperature and make some recommendation about, what do you have to do to be prepared for the day for whatever the temperature is. So let's say we want to do something similar. We're going to store the temperature, but we're going to extend this. So now we're going to know whether it's snowing or whether it's raining. And for this version, let's say that we want to tell the player, the user, that you better drive to school today if it's snowing or it's raining or the temperature is really cold. So let's start out. Let's start out with printing something out again, so we can just inspect what we get when we use this or operator. So we can ask, is there precipitation? Let's ignore the temperature for a second. We're using two pipes here for the logical or operator. What this is going to do is check that at least one of the conditions that we've given it is true. So right now, we said that it's snowing and it's not raining, so that means that we should see true, that there is precipitation. And if we made it so that it was raining and not snowing, still true. One of our conditions is still true. And if I make them both false, it's not snowing and it's not raining. Now it's finally false. There's no precipitation. And I spelled precipitation wrong. Let's fix that. Oh, wait. No, I did not. Turns out spelling is hard. Okay, so we've got our first OR written that allows us to check whether at least one of these conditions has been met. Now we can combine it with our temperature. So let's just do this directly in a conditional. So if our temperature, let's say that our cutoff for where we should start driving to school is 15 degrees. So we can say if the temperature is less than 15 degrees, we're definitely going to want to drive. If it's snowing, we will definitely want to drive. Or if it's raining, we will definitely want to drive. So if any of these three things is true, then let's go ahead and drive. And if it is not, if none of these conditions is met, so our temperature is greater than 15, it's not snowing, it's not raining, then maybe we can walk or bike to school. And maybe this cutoff is a little generous. I don't know that I actually want to go walking in 15 degrees, so let's say 32 is our cutoff. So right now our temperature is 10 degrees and there is no precipitation, so no snow, no rain. That means that it's going to check these three conditions, and if any of them is true, it will tell us to drive. So our temperature is 10, so that's less than 32, so it'll tell us to drive. Better drive to school. If we flip this to 50 degrees, with no snow, no rain, then none of our conditions here are true. Our temperature is not less than 32, it's not snowing, it's not raining, so it should say time to walk or bike. And let's also do one more example. With our OR operator, we've said that it's just checking that one of them is true. So it will still execute even if more than one is true. So all of these are currently true. Our temperature is less than 32, it's snowing, it's raining, so this is still going to execute. Better drive to school today. So OR, checking to see that at least one is true, and is checking to see that all of the ones that we've specified are true. So let's take all of this and put it together into a little rock, paper, scissors game. So we did this previously where we made that like cheating rock, paper, scissors game. Now that we have a little bit more fluency in writing conditionals, and we've learned about randomness, we're going to be able to make one that doesn't cheat, that actually has a random generator in it. So let's go ahead and create a new class. We'll call it RPS game. I'm going to create a public method here that's play, and we can create a new game here and call game.play. So all of the stuff that we wrote previously for testing is now commented out, so we can go over into play and write our logic here. So I'm going to do using static system.console here. Set the title to be RPS game. And let's just get something printing out. And let's keep our console window open. So if we've hooked this up correctly, we should see nothing from the previous examples, and we should see our game logic running. So for this game, let's put the kind of AI aside of how to get the computer to pick a move, and let's just focus on the conditional logic. We'll come back to the AI. So let's say we have the computer's move stored in a variable, and then we'll also have the player's move stored in a variable. This will eventually be randomized to do randomize, and this will eventually be from a read line. But once we have those, we kind of want to express our logic to figure out who won the game. One way to do that would be, without using anything that we just learned about, we could say if the move is rock and the player move was scissors, then we could print out you win. Otherwise, right line, you lose. And then we could do an else if here. Computer move was paper. And the player's move was scissors. Else, right line, you lose. And then do the same thing for if the computer chose, what did I say? Rock, paper. If the computer chose scissors. So this is a lot of branching logic. And it's a lot of branching logic where the same thing happens in the win situation. So here we have the same thing happening here, and here we have the same thing happening for lose and lose. So really, what it would be nice to do is use some of our logical operators that we just learned about to shorten this quite a bit. So what I would recommend doing is pause the video for a second and see if you can think through what we might do here with our and or operators to make this a lot shorter, to express the same logic but in a much simpler form. All right, I'm going to assume that you did that. And what we can do, instead of doing this monster if-else nested structure, is say if, whoops, wrong tab autocomplete there. So here we go. If the computer move is equal to rock and the player move is equal to let's see, if they chose rock, then the player would win if they choose paper. So here we're expressing one of the win situations. We're saying that they must the computer must have picked rock and the player must have picked paper, and that would give us a win. And now all we have to do to get those other situations in here is chain them on with an or. Whoops. So if the player won by playing paper against rock, they would win. Otherwise, let's check here. If the computer threw paper and we chose scissors, that would be another winning situation for the player. Or let's say that the computer chose scissors and the player chose rock. So here are all three of those winning situations joined together with and or. You may be wondering, what is the order of the operations here? And that is a great question. I have a link, I'll make sure that this is in the description, of the precedence table, which tells you the kind of order of operations of all of these things. So you may know, or you may remember order of operation when you were learning algebra, that certain operators were operating before other ones, and you could use parentheses to join some of your operations together. But here we can see that in this table, things all the way at the top have the highest precedence, and things down here have lower precedence. So we can see our not is way up there at the top here in terms of precedence, and our and is has a higher precedence than our or. So if we have ands and ors mixed together, like we do on this line, the ands are going to be checked first, so this will be turned into a true or false. This will be turned into a true or false. This will be turned into a true or false. And then all of that will be joined together with our ors to figure out the final true-false value. If that is hard to think about, you can always use parentheses to help avoid issues with precedence. So now when we use parentheses in here, we are for sure going to execute what's in the parentheses before we have the or that joins all of our and statements together. So the precedence can be tricky, but you can always use the or to sort of detangle that. So here we're just expressing that any one of these win conditions must be met. And if they are not, then we lose. So we can test this. We can see if we put in the computer was rock, we put in scissors, that's a losing situation. We see you lose. Let's try the computer throwing paper, and we throw scissors. That should be a winning situation for us right here. So this should be caught, and we should see you win printing out. Excellent. Let's try one more win. So rock and paper. Oh, wait, did we? No, we didn't do that. We did that in the reverse. Okay, so this should be a win situation. And let's see what happens if we get a tie. You lose. So for this version of our kind of logic, let's kind of ignore ties and let's say that the kind of player loses in that situation. We could just extend this to have an else if, and that checks our computer move equals player move. So if those two are equal, then we print out tied message. And you know what? What the heck? That was simple. Let's keep that in there. So we should see you tied instead of you lose. So let's add in our randomization and our player's read line here. So the easier one to start with is the player's move. So we can do a read line. Whoops, I meant to do a write line here. So what would you like to play? Rock, paper, or scissors. And then instead of just setting it to rock, we can use read line to read in the player's input. And like we learned about previously, if we trim that and convert it to lowercase or convert it to uppercase, that allows us to do comparisons down here in a more friendly way. So if someone accidentally types in space when they are typing in their move and then paper, all uppercase, that turns our string into paper, all lowercase with no space, no leading space and no trailing space. So we should be able to play against rock here and play scissors. We lose. And let's try winning. Paper. We win. So now we can move on to our AI logic, our computer's random logic. So for thinking about this random logic, we need our computer to pick one of three possible outcomes: rock, paper, scissors. And we have learned that we can create random numbers in the dice game. So we can actually, instead of trying to figure out how we randomly generate a string rock, paper, scissors, we can start with just thinking, well, let's generate a random number. 0 means rock, 1 means paper, 2 means scissors. So we saw that we need an instance of the random class. So I'm going to call this RNG for random number generator and create a new instance of the random class. And then once we do that, we can create a random number from this random number generator. So rand choice is rng.next. And here we pass in the minimum and maximum for our range. So we know that we want 0 to be the lowest number, and we said we wanted 0, 1, or 2. And we want to just remember that that max value that we specify is exclusive. So if we pass in 2, we're only going to get 0 or 1. So if we want to get 0, 1, 2, we actually have to pass in that max as 3. So now we have our random choice, 0, 1, 2, and if we want to connect it to this logic, all we have to do is take this random choice and turn it into a string, rock, paper, or scissors. We could technically just come in here and say, was random choice 0 for rock, 1 for paper, 2 for scissors, but I think that it'll be easier for us to debug and sort of look at our code later if we just translate this integer into a string. So what we'll do here is say that the computer's move is an empty string, and we will use a if statement here to say if the random choice is 0, then our computer's move is rock. Else if the random choice is 1, the computer move is paper. Whoops. Else if. Made a typo there. And for the last one here, we'll just do else. Scissors. So one thing I'll note is that I am writing this in a really compressed syntax. You can write, if your if statement only involves a single line of code, you can write that on one line after your if, and that will be the only thing that's included as the body of your if statement. So this is equivalent to this, and it's also equivalent to this. So sometimes you can opt for that syntax. I will also let you know that when you're starting out, this is more error prone than the previous way we were doing it, where we were making sure we always had opening and closing curly brackets. Okay, so we should be able here now to run it and have our computer play against us randomly. And so we should sometimes win, sometimes tie, sometimes lose. What we should do is make sure that we print out what each move was. So let's do a right line. You played and put in their move. The computer played computer move, and hopefully we should see the right things print out. So if we play rock and the computer plays rock, we should see U tied. Let's play it a few times and make sure that's working. Let's play rock. Computer played rock, tied. Well, that was lucky. Let's try rock again. Computer played scissors. We won. That's looking correct. Paper. Computer played paper. We tied. Let's try scissors. Computer played scissors. Tied. You played scissors. The computer played paper. We won. So it looks like we're ending up winning and tying a lot here, and that's how random numbers work, is that this is all possible in terms of the outcomes. If we wanted to make sure that we were testing specific situations, I would just come in and set the player's move directly. Like if we wanted to make sure that rock worked in every situation, set the player's move to rock, set the computer's move to rock, and then run it, then come back, set it to paper and run it, then come back and set it to scissors and run it. We could still improve this in a number of ways. Like right now, this version of our game is not making sure that the player chose rock, paper, or scissors. So if they put in like peace sign as one of those options, then we're definitely going to end up in the lose condition, because none of these could possibly be true because the player's move was peace sign. So what we might want to do to like improve this and take this forward is make sure that we check that what they typed in was either the choice of paper, rock, or scissors. And you can use that or logic that we just learned to be able to do that. So I think I'm going to pause the recording for a second, add a little bit of color and ASCII art into this, and we'll come back, take a look at that, and then wrap up. All right, and jump cut, we're back. So all I did was pause for a few minutes to bring over some things from the previous rock, paper, scissors game we made. So I brought in the graphics that we had in that video, and I set this up so that after you pick your move and we display your move, we call this function display move graphic, which based on what you give it, prints out the associated rock, paper, or scissors graphic. So we turn this into a method so that we can reuse it and use it both for the player's move here and use it for the computer's move here. So with that and a little bit of color and formatting, we end up with something where it's a little bit more fun to play. We got some graphics for us playing rock, the computer playing paper, we lose. Try it again. Paper, rock, we win. So that's all it takes to take our rock, paper, scissors game that we created previously and take it to the next level with using some of our new operators, the and or said that backwards, the or and operators. If you want to keep working on this, what I would suggest doing is thinking about how we created a structure that allowed you to replay the game without having to start it up. So right now, this version only plays a single round, and that's it. Too bad if you want to play multiple times. So think about what we did with the dice game and think about how you might be able to structure this so that you can play multiple rounds and you could keep a running tally of the score for the player. Like how many rounds have you won? How many rounds have you lost? Those would all be great challenges to help hone your programming skills. So that's it for this video. Next up, we'll be thinking about methods.